Hello and welcome to this. Now we're into module 13 and we're going to be looking at this thing called Analysis of Variance, which for the remainder of this module I am simply going to call this ANOVA, Analysis of Variance, the common term for this methodology. What we're going to be looking at now is bringing together a lot of what we studied in Module 10, where we were looking at testing for equality across two means, and we're going to bring in some of the concepts that we learned in Module 11, where we were testing for differences between variances. What this is going to allow us to do is it will open up the door now to test hypotheses that look something like this. So we can have in the null hypotheses as many means as we want, k means, or sometimes called k treatments, and in our alternative hypotheses not all are equal, or at least one of those k means is different. So how do we do this? Well, the hypothesis is a test on means. The methodology is based on partitioning different sources of variation within a data set. So let me just talk a little bit about what I mean by that. In Chapter 11, we looked at two different methodological approaches to looking at the difference between two means. One was simply two independent random samples, where I had so many observations in each of these different samples, x bar A, x bar B. We had our two sample means, and then we tested for a difference between those two means. Now, towards the end of Module 10, we talked about this thing called a matched sample design, where we begin to control for different sources of variation within the data set. So when we transition from the two independent samples to the matched samples, we talked about there being two sources of variation. One source of variation was that which existed within each of those two samples, or in the language of ANOVA, in each of those two treatments. And we talked about the source of variation that exists between those two treatments. And in the transition to match sample, we started to control for one source of variation that in that case was due to differences across experimental units. So we had individual experimental units, and each experimental unit was giving us two data points. And so we eliminated a source of variability due to heterogeneity, or due to differences across our observational units. So we started to talk about this concept of different sources of variation within one data set. So this is the same kind of approach that we're going to be using here now. We're going to, let me just actually simplify this. Let's do a quick little exercise where we have just three treatments. So I choose three because we can use the ANOVA approach for just two treatments, but it's a lot of extra work for very little gain. If we've only got two treatments, it's easier to use Chapter 10 methods. We can use the ANOVA analysis for 4, 5, 6, 10, 12, 20, as many treatments as we want. But all that does, in the sense of illustrating a concept, is it just creates more work. So we'll always work with just three treatments, not because that's what we're limited to, but just because that is really the fewest number of treatments that would require an ANOVA analysis. So what we're going to do is, let's say I have then these three different samples. Now we're going to look throughout this module, we're going to look at a couple of different experimental designs. One is going to be just what we call a completely randomized design. Another is a randomized block, and those two are very comparable to the two types of designs that we looked at in Chapter 10, the independent samples and the matched samples. So here it's the completely randomized design and the randomized block design. And then we'll also look at a third, which is called a factorial design, which is a little bit more complex. But needless to say, for now, we'll keep it as simple as possible. So here we'll have just our three samples, they can have any number of observations. They don't have to be the same. They can be a different number of observations in each. Now, like any other test that we've done, we always enter into the analysis with the assumption that the null hypothesis is true. So if the null hypothesis in this case is true, and mu1 is equal to mu2 is equal to mu3, well then they must all be equal to some common population mean mu. So if that's the case, then the implication is that there's no difference between these three samples. They're all coming from the same population. So what is my best guess of this common population mean mu? Well, it would be what we call x double bar, or the grand mean. And so the grand mean is just the average of that entire data set, treating it as one sample. So with that, now we are going to do this thing called partitioning. We're going to partition this data set into its in this case, two sources of variation. When we get into the randomized block design and the factorial design, it will become a little bit more elaborate. But right now, we're going to partition this into what is called sum of squares treatment, which is denoted SSTR, plus sum of squares due to error, and those together give us sum of squares total. So sum of squares total is really a similar calculation to what you've seen before. The formula is going to look a little bit more complex, but you'll see that it's nothing really different from what you've done before. So this is the difference between individual observations and this grand mean, and then we add those up across all observations. Now here I have to have this double summation sign because I have two subscripts. So what that means is each observation, if this is observation 1 in treatment A, this is observation 2 in treatment A, and so on. Over here I have observation 1 in treatment B, observation 2 in B, and so on. Same for third treatment C. So the notation looks a little tedious, but this calculation is nothing new. You've done these adding up squared differences before. So that's a measure of the total variation in that data set. We split it up into two sources. One is that which is due to treatment, which is the difference between treatment means and the grand mean. So this is j equals 1 through k. So those are our treatment means here, x bar A, x bar B, and x bar C. So that gives us the portion of total variation that can be attributed to differences between treatments plus SSE, which in this case is just a function of individual sample variances. So again, for each of these samples, let me get rid of this circle. For each of these samples, we have a separate sample variance. The writing always gets a little funky when I write down at the bottom of this page. Okay, so there we have our three different sources of variation. Now let me just scroll down a little bit, and I'll give you an idea of what we're doing here. So I'm going to write, let's see, we'll have four bell curves here. So here's what the distribution might look like if the null is true. And I'm going to split the page right here. And here's what the distributions might look like if the alternative is true. Now I'm going to assume it's true to the extreme, so it's not just that one is different. I'm just going to assume, just for illustrative purposes, that all three of them are unique, all three of them are different, which means that we would have then three unique distributions, something like this. Okay? So if the null is true, then it has a mean mu, and all three of our samples, x bar A, x bar B, x bar C, all came from within that one distribution. If the alternative is true, well then I have three different distributions with mu A, mu B, and mu C, and each individual sample came from, came from its respective, that's mu c, came from its respective population distribution. Okay? Now, our estimate or our assumption of the null being true implies that we have a common population mean for which we've estimated our grand mean as our best estimate of that unknown population mean. So on the far left here, if the null hypothesis is true, let's just eyeball that grand means probably somewhere in here. It would be a weighted average of those sample means, so somewhere in that area. If the alternative is true, and I do the same sort of, I'm just going to eyeball it, it's going to be roughly in the middle of those 3 sample means. So maybe somewhere around here is our x double bar. Now we can get an idea of the differences in our calculations just based on these graphics. So for example, if I write out our formula for SSTR again, SSTR was the summation of the differences between sample means and the grand means added across all observations. Oh, I think I forgot a number in there that we have to weight that by the sample size n. I probably forgot that up here too. The sample size nj is in there as well. So if we look at this calculation, SSTR, and we compare the results of that calculation under the assumption that the null is true or if the alternative is true, we can see that we're going to get very different outcomes. If the null is true, those distances between x bars and the grand mean, they're all fairly small. Those differences between x bar and x double bar, so these two values here, and we're subtracting those, if the null is true, those distances are small, so SSTR is going to be small. If the alternative is true, well, now we have quite large distances between those sample means and the grand mean. So if the alternative is true, SSTR is going to be larger. Now, so that's one source of variation, the source that is due to differences across treatments. Now, if we look at SSE as the other source of variation, SSE is simply adding up our sample variances, multiplying it by nj minus 1, and we add those up across all of our treatments. SSE is going to be entirely unaffected by whether the null is true or the alternative is true. It's not going to make a difference. It's based on individual sample variances, so it's going to be an unbiased estimator of whatever is our true population variance sigma squared. SSTR will also be a valid estimator of sigma squared if the null hypothesis is true. If the alternative hypothesis is true, as we can see, those distances are larger, so if the alternative is true, SSTR is going to be very much inflated as a measure of the variance of this distribution. So, if we divide these two, SSTR, divided by its degrees of freedom, which is k minus 1, and SSE, divided by its degrees of freedom, and t minus k, and t is the total number of observations in our data set, so adding up the number of observations across each of our samples, then this is what we call the mean square due to treatments. This is what we call the mean square due to error. Both of these are estimates of the unknown sigma squared, the unknown variance of our population. So here we have MSTR is a chi-squared variable with k minus 1 degrees of freedom. MSE is a chi-squared variable with nt minus 1 degrees of freedom. So the ratio of MSTR to MSE follows an F distribution with k minus 1 degrees of freedom in the numerator and t minus k degrees of freedom in the denominator. So again, if the alternative is true, SSTR is going to be an inflated estimate of variance because these distances are going to be much larger if the alternative is true. If the null is true, then it won't be so inflated. So effectively what we're doing, as much as our hypotheses, if I scroll up, our hypothesis is a test on means, to which you've been programmed at this point. Well, it's a test on means. We're doing a two-tailed test, right? And you've got all of these rejection rules in your head. Well, now we are effectively doing an upper tail f-test. We are effectively testing, is MSTR an inflated estimate of sigma? Is MSTR significantly larger than MSE? If MSTR is statistically significantly larger than MSE, then that gives us evidence that these sample means are sufficiently far apart that it suggests that they must come from different distributions. So, our analysis of variance is a test on means, but we are effectively doing an upper tail f-test to determine whether or not there's a difference between those means or not. Okay, so we'll get into some exercises. You'll see a lot of similarities between the tests on means and the tests on variances. The rejection rules are similar. The p-value rejection rule is very similar. So you'll see a lot of similarities. Often it's the case that it's because of those similarities, because they're not identical, they're just similar, and so it can be because of those similarities that there's a lot of space for easy mistakes to be made. So we just have to be careful when we're going through the exercises. The calculations can be a little bit long and can be a little bit tedious, so I won't blame you if you fast forward through some of the calculations that we're going to do, but you'll hopefully get lots of practice, and you'll see that once you get through the tedious calculations, these ANOVA exercises are really not too bad. Okay, thanks for watching. Let's get started.